This is part 2 of section 4.2, from Math 311, a course on linear algebra at Western Illinois University. So in the last video, we introduced this topic of determinants, and we see that it involved really lengthy calculations, but it gave us a number associated with every square matrix. Now, what good does this number do? Okay, well, that's what we want to talk about. And to do that, we're going to talk about some of the properties of these determinants. Okay, and we're going to see that they mainly we're going to give some informal proofs of this. We're not really going to. I want you to be able to understand the basics of it. You're not going to need to reproduce this on a test or something. In fact, most of these proofs are not going to be real rigorous. We're just going to give you sort of an example and see how, and then suggest how the general case goes. So, first off, maybe I should just remind you how determinants were defined. For a case of a 3x3 matrix or bigger, we define it as this sum, which can be generalized to this sum using the Laplace expansion theorem. Basically, you can pick any row or any column, and then just go along that row or column and compute these terms: the ij entry of the matrix times the ij cofactor, which really is going to be the determinant of the matrix you get by deleting the ith row and the jth column and multiplying that by -1 to the I plus j. All right. And thanks for this Laplace expansion theorem, which is really going to help us along the way. All right. So, first property says that if we have an upper triangular matrix, that's a matrix where all the entries below the diagonal are 0, then we can find the determinant just by multiplying all the diagonal elements. And the idea here, so we want to know why. Well, just expand. We can expand along the first column at every step. Okay, so the determinant of A, in this case, if we expand along the first column, we just have one non-zero entry. It's going to be A11, right, times the determinant of, we cross this column out, this top row out, and we get A22 ANN, and again we'll have some junk up here, and then zeros underneath here. Okay, so that's this. Now we want to compute what this determinant is. And once again, we can choose to take the first column of this new matrix, and this is going to be so this will be A11, A22 times the determinant of A33 to ANN. Okay. And you notice you don't have to worry about the sign because, in each case, this is going to be like the 1-1 entry of this new matrix, right? Or this new determinant. So you can keep going in this form until you finally get A11, A22, like ANN. Okay. So that'll save you some time if the matrix is upper triangular, and in particular, if you have a diagonal matrix, you can just multiply the diagonal entries together and get the determinant. Okay, second property is kind of easy to see. If you have a row of zeros in a matrix, the determinant is 0. Well, why? Well, you can just pick that row of zeros to expand along. So I just expand along the row of zeros. So that's easy enough. Okay, next. Now the next three are going to have to do with elementary row operations and how performing a single elementary row operation on a square matrix, how does that affect the determinant? Okay, Well, in this first case, so let's think of first. Let's consider interchanging two rows in a determinant or in a matrix. How does that affect the determinant? Well, it changes the sign of the determinant. Okay, why is that? Well, let's first look in the case of n equals 2. That's the easiest. We'll skip n equals 1 because there's really no point in talking about that. So remember, if we were to we take this the determinant of the matrix ABCD, this is AD minus BC, and if we interchange these two rows, we get CD AB, and what is this? This is C times B minus A times D, which is the opposite of AD minus BC. Okay, so this is the opposite of AB, CD. Okay. So it's clearly true for n equals 2. All right. Now I'm going to when we have a matrix with 3 or more rows, we can expand any along any row, in particular any row which is not equal to the rows we're interchanging. Okay. So the trick here is so for n greater than or equal 3, the trick is just to expand along any row different from rows I and J. Now, to give you an example, let's look at the case of a 3 by 3 matrix. Let's look at, if we interchange the two bottom rows of a 3 by 3 matrix. So let's say normally we have ABC and then DEF, but I'm going to put the DEF down here, and then the GHI we'll put up here. Okay, so that's going to be the what we get if we interchange the second and third rows. Now we expand along the top row, and we have A times the determinant HIEF minus B times the determinant of GIDF plus C times the determinant of GHDE. Okay, and because we've just proved that this interchanging two rows on a 2 by 2 matrix changes the sign of the determinant, this is going to be minus A times EFHI plus B DFGI minus C DEGH, and this in fact is going to be minus the determinant of ABC DEF GHI. All right, and then now that's what happens when you interchange the second and third rows. You can do basically, if you interchange any two rows, just expand the row which is left over in this case, and you can get the other two cases. And hopefully you can get the idea now, because if you prove this result holds for all n-1 matrices, then you shouldn't have any problem proving it works for n by n matrices, because remember, all the cofactors are going to come from determinants of smaller matrices. So that's the idea here. So a single swap of rows changes the sign of the determinant. Okay, the next operation is just multiplying a row by a constant, alpha. So let's say if we want to find the determinant of A where row I is multiplied by alpha, we can just expand on that particular row. Just expand along the ith row, or the new ith row. Okay, and then you see every term is multiplied by alpha. So hopefully that's pretty apparent. For number 5, let's say we take a multiple of one row and add it to another row. Well, it turns out that that's not going to change the determinant at all. And we're going to do this to show this. We're again going to first prove it for 2 by 2 matrices, and then 3 by 3 matrices, and then hopefully you'll get the idea. So let's say if we wanted to take the determinant of the matrix A plus alpha C, B plus alpha D, and CD. All right. So we've taken the second row of the second row multiplied by alpha and added to the first row. This is going to be A plus alpha C times D minus C times B plus alpha D, which is AD plus alpha CD minus CB minus alpha DC. And these will cancel. And, excuse me. Okay, thank you. Sorry for the interruption. So this is just AD minus BC, which is just the determinant of our original matrix. Okay, and similarly, you can check if you do the other row operation of adding a multiple of the top row to the bottom row. That doesn't change anything either. All right, and then just to see it, and then, well, we won't write all the details of the next thing out, but for so this was the case of n equals 2. For n equals 3, we can just expand just along any row different from rows I and J. Okay. I don't think we have to write anything more than that. Hopefully you get the idea. All right, but those are those for 3, 4, and 5. You definitely want to memorize those, if not the proofs. There's one little tidbit that we might need later on, and that shows if we have two matrices that are the same except in one column, and we add those and take the determinant, we get the same thing as we would if we had added the two determinants. So that, in other words, if A is in the form of some X followed by the column I plus Y, and then B is X, another different column, let's say call it DI and Y, then determinant of A plus B is equal to the determinant of A plus determinant of B. The trick here, if you want to call it a trick, just expand along the ith column, okay, of A plus B. Okay, because if you do that, because then A plus B, so here's X. Actually, let's see, be 2x, and then ci plus di, and then 2y. And all these entries are going to be multiplied by 2, and we can do this. So I think you can see. I think this should work out. Let's see. Okay, we will come back to this. Fortunately, we don't need this too much. But I will say this. This is not true. Is not true in general. Okay. It only works here. It only works here if you have if the matrices are of this form. Okay. All right. All right. Let's go to number 7. says that if E is an n by n elementary matrix, the determinant of EA is the determinant of E times the determinant of A. And the key here is to recall that EA is A with the elementary row operation corresponding to E. Okay. All right. And remember, E is the identity matrix with a single elementary row operation applied to it. So EA is going to be A with that same row operation applied to it. Right. So that's going to help us out. So because E, for in the first case, if E is the identity matrix with two rows interchanged, then the determinant of E is -1. Okay, because the identity matrix has determinant 1, and then we interchange two rows, we get -1, and that's so that's the determinant of E, and then we use number 3. Okay, because that negative 1 there that -1 there is right here. So you can think of this as like the determinant of E, when E is in that form. All right, so we use number 3. In the case where E is the identity matrix, where with with row I multiplied by alpha, then in this case the determinant of E is going to be alpha. Because remember, E in this case will be just like 1s everywhere, with except on the diagonal, except for alpha, and then 0s everywhere else. Okay, but the determinant of E is alpha, so in this case we use number 4. Okay, and that is right here. Okay, so this determinant, this alpha is kind of like the determinant of E. Okay, and then in the final case, where E is IN with let's say RI replaced by RI plus alpha RJ, the determinant of E is just 1, right? Because we do that, we see that this particular operation doesn't affect the determinant either way. So then we just use number 5, and that is basically it. So in this case, we can see that if E is if E top, we can, in this case, we haven't proved, we've proven that the determinant is kind of multiplicative in the case where one of these matrices is elementary. And in fact, A could be an elementary matrix, it's 2. And so this shows that the determinant of, say, E1 through EK is the determinant of E1, determinant of E2, the determinant of EK, okay, for any elementary matrices. EI, E1 through EK. All right. So with that in mind, now we get one of the most important results of this section. If you're going to memorize one of these properties, you want to memorize this one, number 8. It says that A is invertible if and only if the determinant of A is not 0. Okay, so why is that? Well, remember that any matrix can be put in reduced row echelon form by using elementary row operations, which correspond to multiplying on the left by elementary matrices. So we can see that EK minus 1 through E2, E1 times A is equal to R, okay, where R is the reduced row echelon form of A, and, you know, for some elementary matrices, EI. Okay. All right. Now, then from what we talked about here, if we can take the determinants of both sides, and using this result here, I mean, it's not hard to prove that, you know, for example, the determinant of E1A is the determinant of E1 times the determinant of A, and then next would be the determinant of E2 times E1A would be determinant of E2 times determinant of E1A, and so on. So long and short of it is we get the determinant of, well, we'll take the determinant of both sides first. Okay, and then we use that this is equal to the determinant of E. EK, this should be EK. K, determinant of EK minus 1, determinant of E2, determinant of E1, times the determinant of A equals the determinant of R. All right. Again, because we can do this because these are elementary matrices. We also know that they're not 0. Okay, so all of these numbers, all of these determinants here are not 0. Okay, so that means if the determinant of R is 0, that means the determinant of A is 0. And if the determinant of A is not, if R is not 0, then the determinant of A is not 0 either. So we see that if A, now what happens, if A is invertible, then the determinant of R is just the identity matrix. If A is not invertible, then there's going to be a row of zeros in the reduced row echelon form. And from number 2 up here, we showed that then the determinant is going to be 0. So I'll just say if A is invertible, the reduced row echelon form is IN, which means the determinant of R is 1, which means the determinant of A cannot be 0. Okay. And then if A is not invertible, then the RREF, R has a row of zeros, which means the determinant of R must be 0, which means that if this is 0 and these are not 0, then the determinant of A is 0. Okay. So that basically proves it. In each case, the determinant of A and the determinant of R have to be, they're either both 0 or they're both non-zero. Okay, and then finally, so this is going to be very important. And then one last thing before we wrap up. The determinants, it's a common mistake that some students might think of, oh, if you multiply a matrix by a constant, then the determinant is that constant times the determinant of the matrix. And we know that's not true now because it can't be just C times the determinant of A, because that's the determinant if we just multiply one row by C. So in fact, in this case, CA is A followed by A with the following operations, row operations, where R1 is replaced with CR1, then R2 is replaced with CR2, and so on. The RN is replaced with CRN. And so if we look at the determinant, we start off with the determinant of A. Then after this one operation, the determinant is C times the determinant of A. After this operation, the determinant is C squared times the determinant of A. And finally, after the n operations, the new determinant will be C to the n times the determinant of A. Okay, so something to keep that in mind. Okay, it's easy. Once you see this reasoning, hopefully. All right, we will finish up these properties next time.